Okay, let's talk about one of the most interesting fields in physics and engineering, which is the energy approach to solve problems or equations. So this concept is based on the first law of thermodynamics and basically states that energy cannot be created nor destroyed. Energy can only be transferred or can mutate from one state to the other. Okay, so let us go ahead and solve equations with the energy approach. And you'll notice how much easier this would be because you don't have to worry about the coordinate system in the sense that the kinetics in the sense of the kinematic approach, where you have to find the location of every point in space, and sometimes that could be very difficult if the coordinate system is changing um, in time, kind of like in the polar approach. So this is in chapter 13, and we're gonna use the energy and momentum methods. This is just basically continuing with the conservation law of momentum and conservation of energy. That is the first law of thermodynamics, the conservation of energy, which is what I just mentioned. Energy can only change states. You cannot destroy or create energy. There's a finite amount of energy in the universe, even though it's a pretty big amount. Okay. Now, the potential energy of a roller coaster, this is the other thing. There's different types of energy. We have kinetic energy, we have potential energy, we have internal energy, we had chemical energy with this is something that you will see in combustion, in chemical reactions. All right. But in dynamics, we mostly care about kinetic and potential energy. Internal energy, we'll see it in chemistry, but as well in in mechanical materials, where the internal energy, or in thermodynamics, also in thermodynamics, where you want to know how much is the internal energy of a state or a substance at certain pressure and temperature. And this is the concept how boilers work and how we get steam to do processes and liquid water to chill cooling towers because of the internal energy of the substances. All right, let's focus on the dynamic aspect. So the potential energy of a system, let's picture a roller coaster, is transferred or converted into kinetic energy as it moves on the track. Right, so some energy will transfer to heat because of the friction, but because of gravity, the potential energy of having a lot of energy to do work will transfer to kinetic energy because of the movement. And that is the relationship with momentum, because that movement will have a velocity, and as we saw, the velocity of a mass will have something to do with momentum. So in impact tests, the this is an impact test in NASA and or labs. This is, you can put a car, you can put a ship, an airplane. Basically, it's a system that has a lot of energy and is crashing or impacting a rigid body. All this is a very complicated problem, but the energy approach will make it much simpler because you move in a macro scale of the energy of the system is transferred to the energy of the wall. So basically, at the final time, the velocity is zero because you make the wall strong enough to not move. Like in this case, you can see the picture here. The velocity final is equal to zero, so momentum at the end is going to be canceled out. But the initial velocity at a point is very large. So, very large. So we'll see how to do these type of equations. So we already know that everything in this class is about the Newton law of summation of forces of a system, external forces, remember external forces, they're equal to the mass of the system or the combined mass of the particles in the system and the acceleration of the system. This acceleration could be gravity or could be because of turbines. whatever is causing this acceleration, if we care about that force, we're going to study the kinetics. But if we want to know the geometrical shape of the movement, or we want to know the the path of the particle, then we talk about the kinematics. That we know by now. Okay, so this is a vector and this is a vector. This is not a vector, this is a scalar or scalar, meaning that it's just a quantity of magnitude, but vectors have magnitude plus direction. So this basically mass in x, y, z coordinate system, x, y, z coordinate system will be at a point a magnitude of 100 kilograms. Right? This is a system, this is a person, this is a ship, this is an airplane, whatever. Versus acceleration and forces, x, y, and z in the same coordinate system or a different coordinate system, they will have a direction and a magnitude, right? Ax, ay, az. And the magnitude is given by the square root of all these components. Remember? Square root of the squared components. We know how to do this from statics. So this is a scalar or scalar field. This is a vector field. Later on, if you go to engineering, you get your engineering degree in mechanical engineering, electrical engineering, even if you continue studying physics, these vector fields will turn into something called tensors. And if you want to do a little bit research about the tensor approach, is really interesting. Is where you have a lot of information about your system because of the way it behaves. And you can use the tensor approach in correlation with your energy approach. The method of work and energy, let me close this and open again so that we can get rid of those comments. Okay, the method of work and energy. So this is what we're gonna talk about in this chapter. Everything else consider a review, but this is the new concept. So it is very useful because it's related to the force and mass and velocity and displacement. Remember, displacements are the vector x, or sometimes they're u, depending on the book, and they have units of inches or meters. They're just a length, right? Velocities are meters per second, mass is kilograms, force is newtons. We're talking about international system of units. All right, the method of impulse and momentum directly relates to those same things because we can obviously time, because the change of distance in time yields the velocity, gives you the velocity. And with a mass in the system, right, with an airplane in mind or a person or a basketball, that will give us a momentum. And of course, if we're interested in the change of velocity with time, we have acceleration, and then we'll have a force. So all these things are related: impulse, momentum with work and energy. So if we start from the concept of forces and accelerations, we know mathematically we're talking about force equals m, the mass multiplied the acceleration. This is the second law, which we saw already, right? Then the next thing is velocities and displacements. So velocities and displacements are basically integrating twice. If you integrate once, you get a velocity. If you integrate again, you get the displacement. But you can get there also from your work and energy. And we'll see that in a minute. Then in a system, you have energy coming out and energy coming in. So in and out. Think about your car. You have gas in your gas tank, and then that tank gets consumed in your combustion engine, in your motor, your internal combustion engine, and that gets turned into work and also into heat, and of course the residue, which is the exhaust. So let's say gas, which has a value of internal energy, goes into the engine, which is a bunch of pistons if it's internal combustion engine. We're not talking about electrical engine here. this example with gas, obviously it's going to be an electric engine. If you have, I mean, an internal combustion engine, where you have gas, the petrol, the gasoline going into your engine. You have four engines, four pistons, eight pistons, whatever your engine might be. So let's say you have four pistons, could be in V, could be in line. Eight, if you have the system of how the pistons are arranged is not important in this case. That's more for performance and for optimization. But the gas will go into your piston chamber, and with air and the gas at high pressure, it will explode. It will make the piston go down, and that movement will make the camshaft and the axle, all the internal parts move. So that's the work. So you have your state 1 or state 0 transfer to state 2 or state 1. If you start from 0, transfer to state 1. And this liquid octane with gas will turn into CO2 plus H2O. And depending on the type of gas, you have a constant here, or you might have another constant here, like nitrogen, etc. This could be a 2 if it's diesel versus if it's gasoline, or if it's airplane, if it's methane, if it's fuel from some type of octane for airplanes. This part is the yield, or this is what you turn your exhaust into, right? These type of gases. All right, the work is done in your engine so that you can move backwards or forwards, etc. Okay. Now, the velocity and time, because you're going to move this car forward or backwards, and so that takes time, so there's going to be a velocity. The amount of mass of this car is now a problem of the impulse and momentum. So in that case, your equation turns into the mass of the system, which this mass is the same as this, is conserved, even though they're changing state. Because here you have the mass of the octane, and then you have a mass of air into the chamber. But it's a more complicated problem. So maybe I'm choosing a complicated problem here because combustion is not easy. But the point is that the velocities are not the same, right? Once you accelerate, then you're gaining velocity. So V2 could be higher than V1. And basically you're integrating over your force field. So we'll see in detail about this, because this is what we're going to talk about now. These two things combined will give us the whole material that we need to grasp for this chapter. So what is this? This is the energy from state 1 to state 2 is equal to the transfer of energy, the amount of energy in state 2 minus the transfer of energy in state 1, right? It's pretty straightforward. The amount of energy from state 1 to state 2 is the energy that you can measure at state 2 minus the energy that you had at state 1. So let us talk about work of a force. So again, let's start with a force. A force is a vectorial quantity. Force is a vector with a magnitude and direction. All right, so this is an I, J, K. We remember that. And then the direction of the force could be given by the vector r. So in other words, your force F can also be given, is usually written as the magnitude that multiplies your r and x and y and z. Okay, we learned this from statics as well. So given that your r is moving, you're having a change in direction, you're gonna have a change in your force eventually, because the direction changes the force. This is the concept that we talked about in a curved shape, in a curved or better, when your system is on a curvilinear trajectory, the velocity could be constant. Velocity could be a constant velocity, not speed of light, but some constant, say a. Okay, but since you're changing direction, then you have an acceleration. This is a bad example because A stands for acceleration. So let's say velocity u. Okay, your velocity is u, but you're changing direction. So since you're changing direction, your force equals ma, and your a is your value of the constant dr dt, and this is the second derivative. Therefore, there is an acceleration. You can feel it when you're on a road. You're going at 50 miles per hour, and you have your automatic pilot, but you'll feel a force pushing the car outwards. It's because of the change of acceleration. Okay, so let me get rid of these comments. So you remember that a way to express this is with the dot product, which is the same as the cosine of the angle between the force and the direction. Okay, so this is something that we learned from statics. And then the scalar quantity, like mass, is a point in space with a magnitude, versus the vectorial quantity gives you the direction plus the magnitude also. So the dimensions of work are length times force. Okay, so length is going to be in meters, for example, in SI units, and force is going to be in newtons. Therefore, work has units of Newton meter, and the name for that is a joule. Okay, this is joules from the last name of a physicist. All right, so the units of work is joules. Okay, now the units of power, now since we have this, power is joules over second. This is equals to watts. Okay, and so this is power. Is the amount of energy that you do in certain time, or that you have in certain time, or that you use in certain time. All right, so watts is power, and work is the energy, or joules. Okay, so you can have, in a case where you want to find the work between states 1 and 2, where state 1 is the beginning of a curvature, state 2 is at the end of the curvature, you simply have to, if you remember, this is the amount of work is a Newton per meter, right? As we saw before, is the length times the force. What you have to do in this case is do an integral from point 1 to point 2 of your force field times your direction. Okay, and we saw that this is given by the cosine of the angle. So it's very simple, because what you need to do is integrate an angle if it's constant. If it's not constant, then it's more complicated, because you're going to use the argument of a cosine with a changing value. So if alpha is a variable, it turns into a more complicated problem. But if it's a constant angle, like on a road, then it's simple, because cosine is a number, and they just integrate this function, right? And the integral of cosine is sine. Okay, so in the other case, if you have Cartesian or rectangular conditions, you can also integrate with respect to x, with respect to y, and with respect to z. But in this case, you'll be doing your rectangular coordinate system. Okay, and then you find your work with respect to your Cartesian coordinate system. So it's depending which way are you able to find your function. If you can transfer it to a cosine of an angle, or use the delta r, or if you can go back to rectangular coordinates and just integrate each side of your equation in multivariable approach. All right, so the final force is the direction of displacement along the arc S. So the whole area under the curve will be the final force, which is in this case, right? So if they give you the function S in a parametric approach, then it will be pretty simple. So you have basically you'll have 4 ways or 5 ways to solve this problem. One is if you have the r vector in polar coordinates. If not, then if it's constant r, then you do your cosine of alpha. That's the second method. The third method is going to your Cartesian coordinates, or your fourth method is with the parametric surface S. So, as we said, the work of a force is F times cosine of the alpha times delta x. So this is in newtons and this is in meters. And this is the angle. Okay, let's look at this example. So we want to find the amount of energy used to move this box from state 1 to state 2. And the only consideration is the gravity aspect here. So if we notice, since we don't, even though we're moving the box in the x and y direction, now we're not using that approach of statics or dynamics in the kinematics approach. We are using the energy approach, which in the energy approach, we have no energy contribution in the x component. So it's going to be 0. Then we're saying that y is the vertical component and z is 0. Therefore, is negative w, which is w is the mass times the gravity, right? We saw that before. And it's going to be the change in direction across y, from y1 to y2. So the amount of energy that takes from 1 to 2 to move the box is the integral of w dg in the y direction from y1 to y2. In that case, what we have is that this value of w is mass in kilograms, gravity in meters per second squared, this whole thing is newtons, times y, which is in meters. Therefore, check this is in joules. So the amount of energy is given by the mass, the gravity, and the length of the hill, or how much we have to pull it up or push it up. Okay, so this value right here is a value of energy. Like when you design a roller coaster, this is what we have to take into consideration, because it's how much energy you need to pull the cart up. And since this is in joules, you can transfer this with formulas to how many horsepower, if you know how much time it's going to take to go here. If it's 4 minutes, 3 minutes, then joules over time is power is watts, and we can transfer watts because we know that 707 watts equals 1 horsepower. And then you can size the motor, the electric motor in horsepower to pull your cart up. So see how easy this would be. Just plug in the mass times gravity and the height of your hill, of the hill, and that is going to be negative because it needs energy to do that work. It's not going to give you energy. This system needs energy to go up. That's why it's positive. That's what the minus sign tells you. And then if you really want to go forward with the power, you decide how many minutes you're going to take to go up. If you're going to go up in an instant, then it's going to be very high power. If it could be a slow process, then you need less power, but it's going to take more time. All right, so as the example says, we're moving from y2 to y1 if the work is positive. When the work is negative, we move from 1 to 2. Now, let's look at another case. We're still talking about work of a force. So let's look at a spring. So at rest, the spring is not pushed nor pulled, and the say the baseline is right here. At this point, the spring is at rest, nor pushing nor pulling the spring. Okay, so if we press it, we're gonna have a case, and if we push it, if we pull it, we have one case. If we compress or push, we have another case. So let's study both cases. So remember from statics that the force of a spring is given by a constant times the displacement, and this has a linear region, right? Displacement is constant, is proportional to the force. So your displacement is proportional to the force linearly given this constant. If you pull it more, then it's gonna break, right? So the energy from case 1 to case 2, from 1 to 2, is the first distance where you start could be 0 to the second distance, your constant, and the change in x. So you need, when you integrate this, you're gonna get an expression like this one: 1/2 of k and x1 squared minus x2 squared. Okay, you'll see this throughout physics a lot. So this is an ideal spring where k is a constant, and then the only thing that you have to take into consideration is the distances. All right, and it's negative because in this example, it's really important that you notice this. This only applies for example where 1 is at a state where the spring needs energy to deform. All right. So work of the force is positive when x2 is greater than x1. Okay, because the spring is at rest, and in order to be extended, you need to pull the spring. It's different that if you push it, at that case, the spring by itself is going to try to pull back. But in order, a spring, if you pull it, it's not the nature of the spring, then you're giving energy to the spring. In that case, you're not storing energy. Picture the other case. When you push the box inwards, the spring is going to be compressed, so you have some energy stored in here, and it's going to be released once you let it go. But here, you're actually not having any energy released because you will have to pull it. And it's basically the case. So from 1 to 2 is the amount of energy under this curve. Okay, so this is a very common example. This is just basically because of the direction of the force. Okay, F2 may be smaller than F1, and this can be turned into a positive very easily, saying that, oh, indeed, you do have energy, and the spring is going to go back. But it's because of the directions of the force, because it was, in this case, the force is trying to go back. If you notice here, the force of the system is towards the left-hand side. That's why it's negative. All right, so let's look at these examples. We have a spring undeformed, and we deform it a little bit, which is from 0.0 to 0.1. And in this case, we have x2 is a little bit more deformation than x1. So the block moves from A0 or A0 to A1. Is the work positive or negative? And the second question is, as the block moves from A2 to A0, is the work positive or negative? Well, in this case, the first one, from A0 to A1, the work is negative. So in the first case, as the block moves from A0 to A1, we went from an undeformed state to a deformed state where the spring is losing energy, right? The maximum energy of the spring is at this point, the minimum energy of the spring is at this point. So it's losing energy, therefore the energy is negative. But from A2 to A0, now we're at a point where it's going back, the state 2. Remember, we move from stages. So at stage 2, the spring is going back to a deformed position, and because of the compression, the spring is gaining energy to a point where it's flexible again.